So, getting close to the end of the day. For our last talk, we'll have Aris Kafantaris. He studied architecture in the Polytechnic of Athens in Greece and received his master's degree from Kuba Lab in the University of Tokyo, Japan, under the Max Government Research Scholarship. Haris is a chief project manager at Kengo Kuma Associates in Tokyo, where he has been working on international commissions, competitions, and research projects since 2014. His research focused primarily on the documentation and analysis of design languages, coherent compositions rule sets of strategies that are built upon variables such as architectural program, natural material qualities, etc. This research has found application through built architectural projects, investigative installations, and the editing of book publications within Kengo Kuma and Associates. Aris has presented his work, both architectural and media art, in joint exhibitions in Greece, Portugal, and Japan. He has been guest reviewer and invited lecturer at schools of architecture in Japan, Portugal, UK, and the USA. So with you, Aris Kafantaris.
Welcome. I'm going to be a bit redundant and carry my laptop up here because I have my notes.
Thank you, Fabio.
Good. Good afternoon, everyone. Thank you for the introduction and thank you for the invitation here. It's been an amazing 3 days. I'm still thinking about everything I saw. I almost don't want to have my lecture, but it's been fantastic. So here today I'm kind of representing, of course not myself, but not Kengo Kuma by himself either, but rather our whole office. And what I want to do is show how the office has created an environment and a process and an ecosystem through which to design and produce architecture that focuses on the material implications onto design and onto build space. So I have to do double click. So I'd like to talk about the work that we do, but I will not focus on any specific material or a specific project, even though I'll go through 5, 6 projects. I would more like to share what we call our meta project, which we have been building for the last 5 years maybe, trying to organize and codify the research that happens between the projects themselves, which might look disparate, but there is logic behind the chaos. For the last 3 decades, Kengo Kuma has been trying to revive the use of natural materials in architecture and to push back against what he calls the homogeneity of industrialized construction. He also half-jokingly often calls this his fight against concrete. And this is a fight that began before concrete had become synonymous with environmentally unsustainable building practices. Because in a way now concrete is the easy punchback for good reasons. Concrete is standardized, it's scalable, it's weather resistant, and it's almost form independent. So it has allowed architects to consider space in abstract terms and to almost disentangle design from material-specific mechanical and functional limitations. So following this separation of space and materiality, local considerations such as weather patterns and norms of habitation and available resources are gradually being displaced. The same material, more or less, works everywhere. In a way, concrete has become a victim of its own success, and we have become its victims in turn. As a result, I saw a similar picture in another lecture of Hong Kong. This is Tokyo, not very different. Around the world, generic spaces become the norm. And this is a status quo that is very difficult to disrupt, especially when it is backed by a framework of economic efficiencies built into the construction industry itself. So in our office, we have the luxury, perhaps, of having built a narrative that spans 3 decades, where material is the main parameter of design. And I say luxury because this strong narrative often allows us to push our material agenda onto projects. And we often have to be very pushy. And we often fail also to push it. So we want to make a case for material thinking. There are different scales to the story of our material agenda and to how we push it. I would like to start from the small scale and gradually zoom out towards an overview of how we want to rematerialize space. In our office in Tokyo, we start concept design with cataloging local materials, vernacular structures, crafts, and techniques. These are then explored, iterated, recombined, either between themselves or with other systems that we have developed in the past and built. And then this library, it's a physical library, it's also a digital library, it's a library of reference, it grows, it keeps evolving, it keeps expanding. We often start by building material vocabularies, meaning modules or elements, and grammars, meaning rules for combining them into bigger assemblies, that often shape the direction of the project until the very end. This early introduction of the material parameter from concept design has the interesting effect of localizing the design problem before we even start designing. And this is because local materials, as well as their processing and assembly methods, are completely connected to place. In a way, they encode information about available resources, local technologies, weather conditions, and even social habits. And more often than not, natural and composite materials enforce a scale of design and construction that inevitably brings architecture closer to human realities. Unlike undifferentiated solid megastructures, continuous concrete megastructures, for example, assemblies of smaller elements from discrete materials can reframe for us the narrative of architecture as something that is human-centered and built through a collaborative process of making. We can recapture in our own built environment the scale of things, real things, shaped by human hands. Things like bricks, planks, shingles, or tiles. They have all been dimensioned by the inherent abilities and limitations of the human physiology, and apparently soon by the interaction of human physiology with machines, but still they refer back to the human body in one way or another. And of course, the affordances of the body of the builders. I am aware that this is a somehow romantic representation and that what we usually build in cities doesn't look like this, but in a large part of the world, it still looks very similar to this. And this material-centered thought process actually reflects back on the body of the architects too, who unfortunately often find ourselves locked on a desk, behind a screen, behind software that we hate looking at. Because most of the time, there is no standardization of dimensions or structural modeling of new, natural, or hybrid materials. And this means that design cannot take place on paper. It's just impossible. It has no meaning. But it has to be developed through models, through tests, and through mock-ups. From the beginning, not towards the end of the design process. So we often find ourselves on the same table with craftspeople, manufacturers, and structural engineers who need to be involved from the very beginning and not just as consultants. So research and design overlap to such a degree that they become entangled, and it is no longer possible to draw a causal arrow from one to the other. So the result is not so much design through research, but rather design as research. And we wanted to show that. We have been working organically for many years, and we wanted to somehow step back from what we have been doing ourselves and try to contextualize it, try to tame it, and try to see where it could go. So we first tried to show this process of design as research, our meta project, in the 2016 Venice Biennale, reporting from the front. The topic of that Biennale kind of put a mirror in front of architects and asked us to face our responsibilities and say, what are we doing to make ourselves relevant? So it was a good excuse for us to start thinking about it. We made a selection of about 30 small experimental pavilions in order to show the links between projects. So we showed structural systems that were developed and adapted through trial and error and evolved from one project to the next. We followed these systems as they changed in scale and material incarnations, and we organized them into families. We call them tectonic families. And the way we organized it was in families that were called, for example, here at the top, stacking of planar elements, and at the bottom, weaving of linear elements. So in a way, we thought in terms of geometry and process of combining elements into a larger structure. So this was the first attempt at seeing our projects as embedded in a framework of research. I need to say, there is also a real evolutionary relationship between many of those projects. It's not that we just put them together, see what looks like what, and then we showed them together. Literally, we would take a mock-up from an unfinished project that was still ongoing, then bring it to another design team, and they need to do something else, but they need to do it in another material. They would try to use it, and it would become something else. So for 2 years following the Biennale exhibit and until 2019, we tried to clarify and expand these genealogies and to document and communicate how the projects were connected between themselves. Some projects were direct evolutions of other ones, while others were born from our attempt to modify a system in terms of scale, material, or structural role. The result was a large retrospective exhibition in Tokyo Station called A Lab for Materials, where the showpieces were not buildings. We were not showing buildings at all, but families of materials, assembly patterns, and construction techniques illustrated through large life-size mock-ups. Often the same mock-ups that we had used in construction sites. If they were still in Tokyo, we used them in this exhibition. Unlike the more limited Biennale exhibit, this research tried to cover almost all of Kengo, Kuma & Associates' built work. And to place it in one overarching diagram, a taxonomic tree that you see here, where we could call them genetic relationships in a very broad way, do not exist among different versions of the same system family only, but also laterally across systems. What we wanted to show with this exhibition and with this tree diagram is that the implementation of new material methods does not happen really individually within the confines of each project, but that there is an underlying network of previously tried ideas. And there is an iteration on this network that produces new nodes and experiments that potentially can grow this tree. In this tree, we included as much of our build work as possible, about 107 projects. We organized them by material and operation, and we tried to highlight internal narratives of evolution, both vertically and horizontally. So you can see that it iterates through materials: bamboo, wood, paper, earth, stone, metal, glass, tile, resin, and membrane or fiber. but also across the different vertical families or tree branches, lateral lines are connecting projects that represent jumps, meaning a change of material under the same module or assembly logic. Like, for example, the thin panel triangular lattice systems, which we had developed about 2 years apart. One is called Polygonium and is in extruded aluminum with aluminum sliding joints. And the stone cart castle that came a bit later was done in Pietra Serena with local craftsmen from central Italy in a completely different context. And of course, different joints and different implications. And then, running across the different material families and linking them are the methods for combining elements. We call them particlizing, weaving, reciprocating, which I probably forgot to highlight, wrapping, and stacking. I have to say, to emphasize that the categorization into these taxonomies is not strict. This is not a scientific classification. It kind of emerged intuitively as we talked about our own projects out of a process of employing materials in human-sized units, like sticks, panels, tiles, loops, which are then combined through assembly operations into larger aggregations. And then they work as furniture, partitions, facade envelopes, or building structures. So we rather prefer to use this diagram as a map that traces the lineages of material research and the affinities between the projects, both past and future. But most importantly, we use it to make the point that design, especially a material-centered, more I don't know if I should use experimental, a material-centered, non-standardized design process is inconclusive and continuous. And every new node in the tree diagram just poses new questions. None of these is finished, and none of these is perfected or finalized. So the entire tree goes through 107 projects. And I would like to take you through one of the sub-families, which is perhaps one of the most recognizable ones, the one we call wood stacking. It could also be called wood weaving because it combines the stacking and weaving processes, mostly. And we can follow the wood stacking lineage and observe in, I wouldn't say in real life, live, sequentially, how a construction system inspired by a traditional toy develops, it scales up, it warps, it becomes a screen, a structure, a framework, and finally switches material to become something completely different in the span of 8 years and 7 projects. The wood stacking family started with a fascination about a traditional joinery system. The system is called chidori, and it was originally used as a novelty. It wasn't a structural system, it was used for screens. And nowadays for the creation of a wooden puzzle, a toy puzzle, in Hida Takayama, which is an area in central Japan that is famous for very sophisticated carpentry. So in Mumaya Valley, in Hida Takayama, one of the earliest examples of this joinery system is still preserved in a small repository. The story goes that in the early 1600s, a master craftsman created a screen door that no one could understand how it was put together, until a rival carpenter that couldn't stand this anymore snuck behind the screen and cut it open. And he understood the joinery. We know the name of that carpenter, Jinbei Okada, because he popularized the system and started building it everywhere, mimicking the original method and thus making it very popular in Takayama. Looking at the screen, which is the one on the right, it's the small screen inside the building, one can immediately see that the wood members are interwoven in a way that looks like a fabric weave. seemingly defying the thickness and rigidity of the material. The rather normal and standard half-notched wooden screen in the center of the repository almost stands like an intentional counterexample. We don't think this was curated, but it does the job of explaining the difference perfectly. So this type of screen eventually became the popular toy puzzle, which is now sold in temples and souvenir shops around Takayama for about 5 to 6 euros. By studying the small Chidori puzzles, we can understand how it has been possible to seemingly weave woven sticks as if they were fabric. The system is composed of identical notched sticks that are used in 2 directions, which we call warp and weft, as in a fabric. And here the important innovation of the Takayama carpenters was that the notches are deeper than they need to be. They're not halfway through the wooden stick, but 2/3. This means that we can interchangeably place half the warp and half the weft sticks until we cannot place any more sticks, of course, without bending them, seemingly. But because of the extra space that we have on each joint, we can lift the whole assembly from the central stick. And then we have exactly enough space in the center for one last stick that is called the lock. If you see on the bottom left the picture of the toy pieces, the last piece is slightly different. The notches are 1/3 through the stick, not 2/3. This means that once we slide it in and push the whole assembly down, it locks. And it interlaces into the Chidori weave. And of course, the opposite process is needed to disentangle it, but if you don't know exactly what stick is what, you can spend a lot of time pushing them around until something moves. This system was used for 2-dimensional screens originally, but variations exist in Takayama where a 3-dimensional joint is similar created. It's the one that looks like a 3D cross. There are many different flavors of this. So this XYZ joint made us, intrigued us more than the screen, because it showed us the possibility of creating a wooden structure that can be locked and unlocked into place without any tools, without any nails, without any additional components. Because also, there is this narrative, correct narrative of Japanese joinery, structural joinery that is assembled without nails, but structural joinery locks in place. It can still be disassembled, but these joints were different. These joints were intended to be disassembled by a single person, like a toy. The logic of the 3-dimensional joints is similar to that of the 2-dimensional screen. We have 2 directions that weave through each other, and the 3rd direction acts as the lock. So the assembly starts with the warp. Then we put the lock element and we rotate it into place just enough so that we can slide the weft all the way in. And then the pivoting lock part can rotate again, and we end up with an XYZ cross joint that is invisible. It's less stable than the 2-dimensional joint, and this is something we had to deal with eventually. But as architects, we were deeply intrigued by this idea of an invisible joint that locks into place just through some 3-dimensional manipulations. So we really wanted to make something with it. We wanted to make a pavilion. And we got our opportunity in 2007 with an invitation to build a pavilion for the Milano Salone. The pavilion was made of continuous sticks with several notches for the intersecting nodes, but it was very challenging to put together. Unlike the traditional Chidori screens or cross joints, here we have many different sticks, many different lengths that correspond to this organic outline that we wanted to make, both the exterior envelope and the hole inside this wooden cave. So in order to manage the complexity of this assembly, we had to create two-dimensional sections with their respective instructions, slices of the pavilion if you want, and then we had to lift them vertically, support them temporarily, and then bring the third direction and rotate them into place. It was acrobatics with many workers. It worked, and the final pavilion was very lightweight and transparent, but also very pliable and fragile, due to our decision mostly to maintain fully operational joints without permanent fixations. So after the exhibition, with only a few strategic twists of the members, the pavilion joints unlock and it just breaks apart into the component sticks. So the Chidori system was clearly applicable on an architectural scale, even if it's a small architectural scale, but it left many open questions as to its structural capacity. Bonus points if you can see the extra support stick because the pavilion was bending. It's a bit hidden in this photo. So for this reason, we wanted to try and apply it to a full-size building and push this joint system to structural sufficiency. This happened in 2008, a bit more than a year after Milano Salone, when we got the opportunity to design a museum and exhibition space for a dental clinic in Western Japan called GC Prosto Museum. We ended up building almost the entirety of the museum using 60 by 60 millimeter sections of wood with a small core buried inside, done in conventional construction. One of the main lessons of the Chidori Pavilion was that there is a price to be paid for the mobility of the joint. The entirety of the section of the wood member, as you remember the joint, is not used structurally because we have removed most of it. Only 1/4 actually transfers loads across the joint. So what we had to do, because of this reduced structural section, we increased the size to 60 by 60 millimeters, while in Milano it was half the size. And we decided to immobilize the joints after assembly, permanently locking them into place. So the entire structure was organized in sub-blocks that were sufficiently rigid, and they were connected to each other through a slotted joint system that is slightly visible at the ends, at the fringes of the block. So we did use the modularity and the mobility of the joint to make the bigger modules, but then we locked them into place. Of course, extensive structural testing had to be done since the loads, this was a real building, and the loads would be distributed to hundreds of individual small members, which is very different to the standard strategy of having a few concentrated columns, and it's rather atypical. So we had to research this almost from zero. GC Prosto was one of the first projects where we started realizing the synergies that can be gained from this kind of porous material envelopes, where architectural elements no longer perform single roles. And the sticks are not only supporting the building, but they also function as window frames, furniture, and display cases. And almost everything is expressed through a single continuous system. So in the end, we had to give up joint mobility for structural integrity. But 3 years later, in 2011, circumstances allowed us to use Chidori in its original form as a deployable system that can be disassembled. In 2011, a devastating earthquake and tsunami hit the coasts of Tohoku, causing large-scale destruction in urban and rural areas alike. And as a bonus, it exploded a nuclear power plant too. And a few months after the disaster, Japan was still trying to cope with everything. East Japan Project was formed. East Japan Project brought together designers and architects from all over Japan and paired them up with craftspeople from the region of Tohoku. We collaborated with the artisans to develop novel items that made use of local materials and the human expertise, offering support and increasing the visibility of the recovering communities as these items were then sold into museums, galleries, boutiques. Tohoku region is famous and it has been traditionally associated with small-scale craft manufacturing. So we decided to work with the local carpenters and make a furniture system based on the Chidori joint. So we reintroduced the rotating joint function that allows quick disassembly. But unlike the Milano pavilion, we standardized the stick elements and brought modularity into the system. So we now had a set of 12 equal length sticks, if not identical, because we had 3 different kinds of stick roll, the warp, the weft, and the lock, plus plate wood surfaces. And this would be enough to assemble a self-sufficient Chidori furniture module. The module is cubical, and its edges extend by half the size of the cube. So we then connect these spiky cubes with simple wooden plugs into larger assemblies and different combinations. It was really a simple cubical grid, but the flat panels that worked as shelving also helped us create rigid planes and help the whole thing stand much better than the original Milano Salone pavilion, which was quite shaky. In parallel with the development of this furniture system, we started exploring more radical variations. The space that we had created in GC Prosto Museum, this wooden lattice spreading like a transparent cloud of solid elements, was something that showed us a lot of possibility for future design iterations. So we wanted to explore that more and to investigate the idea of a dispersed, particleized, this is an invented word, but we use it, particleized structure, or a particleization of architecture. And we got the opportunity to do this in 2011 when we were asked to design the interior of a Starbucks cafe in the historical area of Daisaikuku in Fukuoka, in the south of Japan. The main challenge was how to draw people inside a deep and narrow space with a very small face to the street. So we wanted to use a grid cloud, like the GC Prosto Chidori system, in order to create an environment, a ceiling, and the shelving elements. But there is, of course, a problem with cubic grids. They are not directional. They are static. So we try to deform the cubic Chidori into an oblique three-dimensional lattice, diamond-shaped, and to give it a sense of fluidity, but also to give a very different perception of its density and shape according to how it was approached by the people. It wasn't as simple as just deforming a cubic lattice, we soon discovered. So we had to start rethinking it. So orthogonal grids have the wooden members crossing at every intersection, like 3 wooden members. But this oblique grid ended up having 4, which necessitated wood joinery of greater complexity. And actually, we ended up using steel dowels, sandwiching the 4 members together. We had to simplify a bit. So we broke the grid apart into smaller elements, maybe closer to what we did with the Chidori furniture system. And these elements look like X-shaped butterflies. You can actually see them. So these butterflies are joined to each other, and each of them is joined to 4 other butterflies with these steel joints. The sticks are 60 millimeter square in section, like the GC Prosto Museum, exactly the same. But the joints are fixed from the beginning. There was never any mobility there. They cannot be disassembled by hand. This oblique grid had a very beautiful lightweight appearance, but it also had a very obvious drawback that we wanted to deal with in another iteration of the system. Because of the way the modules are joined together, and this is something you can see more in the left picture in elevation, there are no continuous linear elements throughout the whole structure. The elements are interrupted. This means that if you want to load this structure, you cannot effectively transfer loads. It will collapse. The joints will break. And we wanted to use it as structure. And we wanted to use this directionality that it has in order to create a structural direction to the system. So we rotated it 90 degrees. And then, of course, we had to redesign it. In 2012, we were invited to do a pineapple cake shop in Tokyo. And it was one of those dream clients that lets you do anything you like. By rotating the oblique lattice of Starbucks coffee by 90 degrees and creating a vertical framework, we transformed this lattice into a structural system to take loads for a small 3-story building. But of course, rotating was not enough, because as you saw, there was no continuity, and we had to redesign it. In order to redesign it, we went back to the source, the original 2-dimensional Chidori frame. We created these lattice surfaces that lock into place exactly like the original screen system, with weft, warp, and lock members. But unlike the original, these are deformed into a diamond lattice, which comes into play later. Also, as opposed to the previous iterations, if you see the diagram of the building, we also try to vary the scale of the lattices using a variety of densities throughout the building, depending on the architectural role that they would play as dividers, facade elements, or even in interior furniture. It was a continuous system, but with variations. And like in the Starbucks cafe in Fukuoka, this wood system, this wood joint system, would have 4 sticks coming together at each joint, but with a slightly different arrangement. So the structural walls are comprised effectively out of 2 of the screens that you saw, the diamond-shaped screens, in parallel, sometimes even 3. And then we introduce 2 more directions that are interlaced and lock the whole thing and make it possible to transfer lateral forces as well. So it works as one body. And we started calling it an exoskeleton, actually, because for us, it stood in opposition to the more usual way of supporting buildings with a vertebrate skeleton with internal, rigid, concentrated bones. And instead of that, we have a dispersed structure that works around the building, that is not separate from a facade, dividers, or furniture. But supporting a 3-story building, of course, required stronger joints than the one we used in Starbucks. Just piercing everything with a steel dowel would not do it. So we had to go back into Japanese joinery, and hopefully there was a kind called Jigoku Gumi, which translates into hell joinery. I'm not sure if it's hell for the carpenters or for the users. And it was used for connecting diagonal elements, for reinforcing structures and fittings. So this technology still existed, this knowledge still existed, and we used it to connect 4 different structural members that crossed a node and continued in different directions, different oblique directions. This building, the Pineapple Shop, Sunny Hills, it was in a way a pinnacle of structural complexity for us and our office. And we felt that it pushed this 3-dimensional lattice to its limits. So what we sometimes do when something is interesting but becomes too complex is we step back and then we try to see if we can do something similar but simplified. And this is what happened after the Pineapple Shop. We asked ourselves if there is a way to have directionality without having to revert to hell joints. This question led to the development of Eure Pavilion in Paris in 2015. We created this temporary pavilion using linear members, just wooden sticks, arranged in an oblique three-dimensional lattice, like Starbucks and like Sunny Hills. But there are some significant differences. First, we use sticks that are rectangular in section, 90 by 180 millimeters, not square. Rectangular section sticks have directionality. They have density directionality. And we wanted to see if we could imbue an oblique lattice like this one with different densities. So the rectangular members, as I hope it's clear from these pictures, allowed us to modulate the transparency of the structure depending on where it was viewed from. But still, this was much, much simpler than the previous two systems. We abandoned the complex three-dimensional Boolean intersections of the pineapple shop, and we tried to work with rotation. So periodic rotation of the members creates a spiral module. And this spiral, as it ascends, is connected to 4 other modules in different points. But still, the joints could be greatly simplified because first, of course, the structure only needed to self-support. It's not a building, it's a pavilion. And then we managed to only have 2 sticks meeting at any given junction, which meant that we have just a planar 2-dimensional joint solution with a half notch and nothing special, really. This obliquely braced structure was pretty strong, and it was undulating, almost like a flame, changing really appearance as one moved through it and around it. At the same time that we were working on Eure Pavilion, we received an invitation to create an outdoor installation in Milano Salone, again, by a manufacturer who wanted to push the limit of their product. It just so happened that the manufacturer was a stone manufacturer, and their main product was marble. And these things often work circumstantially. There's no plotted strategy behind, but we try to see if we can do the same thing with marble, and to see if we can have it behave as if it were wood. The result was stone forest. With stone forest, this lineage, the Chidori lineage, went full circle, and it arrived back to Milano 7 years after the original wooden pavilion, inspired by a wooden toy from Hida Takayama. In the previous years, we had developed several projects out of wood using traditional Japanese techniques and also contemporary fabrication technologies. This is something that I have not shown, but we do work a lot with craftsmen, and the level of quality and expertise of manufacturers and contractors in Japan is extremely high, but we're doing architecture, not craft. So we work with CNC, we work with robots, we work with anything we need to. It's always part of the process. We use all the tools. So of course here we had to use CNC milling of marble in order to put this together. Here we wanted to explore the same techniques, the wood notching techniques applied to the marble, and to see if we could create something very light out of a mineral material, Carrara marble in this case. But of course, marble behaves very differently. It is a very interesting material, actually. It's structurally quite decent for a stone. In Greece, in the Parthenon, there are marble beams 4 meters in span. So it has tensile strength. But being stone, it's also very, very brittle. We wanted to see how small we could get with these elements, and we managed to go up to 9 by 9 centimeter sections, which were first joined like the Eure Pavilion with half-notch joints. The thing is, what works as an advantage in wooden structures, which is a very tight fit between the wooden members, was a drawback here, because a slight torsion would channel forces into the marble, which is brittle, and it would break. So we needed some sort of relaxation. And in the end, our engineers proposed that we use wood. And we loved the idea that we had abandoned wood to make a marble lattice system, but then we had to reintroduce wood as a joint so that it could absorb the forces that marble could not, and the small fluctuations. And it was almost the opposite of the Starbucks lattice, where we used steel because wood was insufficient. Only 2 elements met at any joint at any given time. But of course, the interlacing of all the elements created a structure that was quite strong. We also had to send a small wooden mock-up together with assembly instructions to make sure that the correct order of operations was maintained. Because this is an interlaced structure, if the builders just started putting it together without minding the order, they would find themselves at the end locked out of it without being able to place the final elements. So this genealogy started with a wooden toy, and in a way it culminated with another wooden toy 7 years later. And the original 2-dimensional chidori, which had already evolved to a 3-dimensional joint when we found it, it became a lattice with several nodes. The lattice grew, it became structural, then it was deformed to achieve directionality, but it lost its structural properties, only to find them again soon after by changing direction and changing joint system, and becoming variable in density, to then go through simplification and more density variation and make a final jump to a different material. Most architects who have tried to introduce new materials in commercial projects, I think, will testify to how much resistance there is. Clients and contractors, they push for rationalization and simplification, and projects are driven by costs and schedules. At the same time, untested materials and constructions tend to fail in unexpected ways, and they fail a lot. They demand iterative designs through trial and error. They also age, they require maintenance, replacement, and recycling. So why do it? The case for natural materials is often framed in terms of sustainability, like it has been in these 3 days, and it should. Local materials are usually less processed and don't need to travel large distances to the construction site. But for us, what we call material thinking is not only a matter of quantified energy footprint or carbon gains. It's about a deep shift that obliges us to ground the design into its context, to build in a human scale, creating spaces with gradations, ambiguity, and warmth. So architectural considerations, I would say. And then to bring back a culture of collaboration, both in design and in construction, which is getting lost. And finally, to also frame architecture as an enterprise, as a continuous open-ended research that is better understood as a set of iterations, as a series of iterations, rather than a finished product. So the lifetime of a single design project will rarely be enough to develop and perfect a new structural system or a new material application. At least this has almost never happened for us. It will be enough, however, to try to test and apply this partially and to explore further onto new projects. Failure or partial failure is common, but the small successes help normalize the idea of using natural or non-standard or composite materials and stepping away from the comfort zone of mass-produced, mass-designed, catalog-sampled architecture that is disconnected from its natural, cultural, and material environment. This is why, for us, the work of the office is much better encapsulated by this tree diagram or map that we did 4 years ago, more than by any individual building. And since we did put this map together 4 years ago, it has expanded. This is already obsolete by a lot. And our hope is to see really similar maps springing up in architecture practices around the world. And then perhaps we can start joining all the maps to a larger roadmap. Thank you. Yes.
To Aris.
I moved to the shadow because these are like the sun.
You're suffering. Any questions? No? No one? Well, I can try. Aris is in the stage, so no one is asking things, I guess. So one question for you. We can see that although the office is very experimental, so you have all this plan that you're following, but at the same time you have these very corporate clients, Starbucks, Sunny Hills. How does the office manage to keep the track of this strategy? At the same time you have to deal with these dozens of clients that I can imagine are composed by boards and very bureaucratic decisions. So how does this work, in the office structure? How do you manage to keep this going?
We have an advantage that we try to overplay, which is that we have already built this, not the tree, not my face, the tree. We have already built this image. Some people would say brand, which is a word I hate, but we've built this image of an office that works with natural materials or new materials, not just natural materials, and brings value out of that. So often, even corporate clients that come to us, they have a sense of respect for what we do, and very rarely would they ask us to do something that would be atypical, like a large concrete building with a panelized aluminum facade. It sometimes happens, but often there is a certain level of respect and understanding. On top of that, I'd say working in Japan has some unique advantages. I'm sure this is not only in Japan, but especially in Japan, the manufacturers and the builders, they have a very strong personal sense of pride and shame. So we often find ourselves going to them with something that looks ridiculous, and they make it work. While outside of Japan, we found this, but it's much harder. It's much more common to go to someone with something ridiculous and they tell you it cannot be done. So this environment of manufacturing and construction helps. And it's not low-tech, that environment, I have to say. It's really an interesting overlap of low-tech and high-tech. The culture of joinery exists, human hands exist, but then so do robotic arms and CNCs. So this is more or less how we deal with it. And also, of course, I have to say we try to be very pragmatic, and sometimes we have to make small wins. So we start a project, let's say, proposing a large structural system that is composed out of hybrid sandwich elements between perforated steel and plywood, which is something we actually did. And then pretty soon, for different reasons, usually budget, client says, you can't do this. Then we try to do this in the smaller part of the building. If we cannot do even that, then we try to transform it into something. So you'll see a lot of projects that are partial,
Yeah, sure.
but that's how we move ahead.
Okay, great. So, yeah, one question here.
Thanks, Aris, for the nice way to tell this story. I have a question on one point. At a certain point you said that for you it's very important to team up or to talk very early to the contractor, to the craftsman, even beyond being, advised by them. What means collaborating, doing something together. And it makes fully sense, if with your claim, or the practice of the office and so on. But at the same time, my personal experience is this is a very nice thing. but only works with small projects. And it definitely fails with public projects, just because you're not allowed or not supposed to talk to anybody, at an early stage. Even if these people would do it for free, what is rare, you're not allowed. And this, how do you in the office deal with this paradox, that where you absolutely know what the advantage is, both, at the end you can have a nice project, much cheaper, and so on, but you have to, find out about these means of production very early in order to make the right decision.
It's like you say, what we sometimes do, if we don't have access to this network of people, is we do it with our own network of people. We do it with our own engineers, we do it with our own craftspeople, and then later on in the project, when we build up those networks, we go to them saying, the Japanese say we can do this here. And often they say, no, you can't. But sometimes they say, maybe. And then we start this conversation later on. But you're right, it's like this. The smaller projects give us much more freedom. It's also about regulation. And also, stepping back, it's different in Japan. For some reason, we can do much more in Japan, because we already have the networks, even if it's a public project, even if it's a public competition. It's a big country, but at the same time, it's very interconnected and it's very, very interwoven. So we know we will be doing a competition in Hokkaido. Already, there is a notion from some other project, what is being made there? Who makes it? Let's start talking to them. But if it's in Switzerland, then no. Even though we actually have some projects in Switzerland and we have our people and we would approach them, but this often doesn't work ideally.
Great. So, yeah, another question there in the back.
Hello. Thank you very much for the amazing presentation, Aris. Out of curiosity, so it was interesting how you started in the beginning of the project as an analog method of building, of the toy. Now looking at the projects that are going at Kengo, Kuma, how is it now? Is it now more towards the digital? Because it seems, in the presentation, and in general, the projects.
Yes. Long story short, we try to work with small elements. We try to create elements and to find grammars and to combine them and make meaningful systems out of them. These can be simple. If it's an XYZ cubic grid, it's something you can design and you can define almost by hand. But the more complex these become, the more counterintuitive, time-wise, it becomes to have people drawing them up, like with examples we saw in the previous lecture. So we use digital methodologies a lot. Half of the office uses Grasshopper. Also, because Kuma-san was teaching in the University of Tokyo for many years, we have very close relationships with some labs that work in fabrication and in digital fabrication, like Obuchi Lab, which was mentioned in one of yesterday's lectures. So we use these technologies a lot. At the same time, we might, let's say, for the pineapple shop, this was designed in Grasshopper. The length, the pieces, like the cataloging of all the pieces was done in a very standard, I would say, parametric design workflow. But to design the joints, we had to talk with the carpenters to tell us how you're supposed to join this. And there was this overlap. But we cannot do it without digital tools. Hands down, I have to say this.
So, any last question? No?
Thank you.
Well, Aris, thank you. Thank you so much for coming.